In this class, I would like to talk about complex numbers. Look at the following. X plus 1 equal to 0, x square minus 2 equal to 0, x square minus 1 equal to 0. I have three equations. If I look at these equations, I have x equal to minus 1. Minus 1 is a root for this equation. X square equal to 2, so x equal to plus or minus root 2. And this is x equal to plus or minus 1. If we carefully look at these three equations, for the first equation you have only one root, namely minus 1. For the second one you have plus or minus root to two roots. Similarly, you have two roots for the third equation too. Can we solve an equation of this type? We don't have square of a negative number. There is a negative number minus 1. The square is not yet defined. X square equal to minus 1. So if you look at this kind of equation, then x square equal to minus 1 will give you another information that if there exists a root, for x square plus 1 equal to 0, then it is called an imaginary number. It's called an imaginary number. And imaginary number is denoted by I. Denoted by I. Look at this. Again, I'm writing about the complex numbers, and I have the certain equations. I could solve these equations, but I could not solve the equation in this n. If I see n, w, z, q, r. If I see this, I have, now I want to, I can find the roots, all these roots in R. So there is a number which has no root in any of this field. So now I have a definition for a complex number. A number z equal to a number x plus iy Now I have the following definition. A number of the form x plus iy, where x, y are real numbers and I square equal to minus 1. Now I square equal to minus 1 means I is some number whose square is minus 1, which is we are defining. So I square equal to minus 1, the imaginary, and I square equal to minus 1 is called a complex number. A number of the form x plus iy, where x and y are real numbers and I square equal to minus 1 is called a complex number. So a typical example, let us see this. 2 minus 3i, 2 plus 3i, minus 2 plus 3i, minus 2 minus 3i. These are all examples for complex number. This is a complex number, this is a complex number, this is a complex number, and this is a complex number. Now, if you see this, I want to make a note. Any real number can be regarded or can be viewed as a complex number. Any number can be viewed as a complex number. Any real number. How? Let R belongs to R. Take a real number. Then R can be written as R plus 0i. 0 into I is 0. So R can be written as R plus 0i, which is a complex number. Is in the form, hence R is a complex number. Let us see, and before this we write let z is equal to x plus iy be a complex number. Usually we write z in this form, and z bar is x minus iy. I have taken a complex number, I am writing z bar. Z bar is x minus iy. Z and z bar are called complex conjugates. They are called complex conjugates. That means z is complex, z is conjugate to z bar is conjugate to z. So again, a typical example is 2 plus 3i. If you take a complex number 2 plus 3i, 2 plus 3i is a complex conjugate of simply conjugate. Complex conjugate of 2 minus 3i, and vice versa. And vice versa. So let us see a small. What is z bar? I mean, so far we have not defined two complex numbers, product of two complex numbers. But let us see what is x plus iy into x minus iy. What is this? This is x square minus iy whole square. A plus b into a minus b is a square minus b square. So you will get x square. This is minus I square y square, which is equal to x square. Minus I square is plus 1 plus y square. If you see this, every complex number can be represented in a plane or on the plane called Argand plane. So every complex number can be represented as a point on the plane. This, now we don't write like x-axis and y-axis. This is a real axis. What we say is real axis, and this is imaginary axis. And this is origin 0 0. Why I have written 0 0? Instead I can write down 0, but let me see why I am representing 0 0. The first one is complex number is written as every complex number can be represented in a plane called Argand plane. Now 2 plus 3i can be represented as follows. This is 2, 3. 2 units, 3 units. So this is real axis. again you can extend it in the same fashion. You can represent minus 2 comma minus 3, and here minus 2 comma 3, minus 2 comma minus 3. So in the same as we have done in a Cartesian plane, we are doing it in the organ plane. So any complex number can be represented by a point. Now again I will reframe the definition of a complex number. I mean I can make it as a note. A complex number a plus ib, where a and b are real numbers, and I square equal to minus 1, can be regarded or can be viewed as a point a comma b. Now I have a definition for C as the set as a comma b, where a and b are real numbers, and I square equal to minus 1. Remember, there is no I representing in the set C. So I need not write actually I square equal to minus 1, but for emphasis, for emphasizing this, I am writing like this. A comma b belongs to R. And even if you ignore I square equal to minus 1, there is no harm. So AB belongs to R, which is nothing but R square. So every complex plane can be regarded as a product of R comma R cross R. Now after looking at this, let us see the representation, another form. Let z equal to a plus ib. This is the usual way of writing a complex number. We'll write z, z1, z2, z3 and so on. So a plus ib. Z equal to a plus ib. Then z bar is a minus ib is called the complex conjugate, or simply conjugate of z, and vice versa. Means if z bar is a minus ib or z equal to a minus b, z bar is equal to a plus ib. So if a plus ib is a complex number, a minus ib is also a complex number called complex conjugate. And every pair of, complex numbers occurs always in pair of numbers like conjugates. So a plus ib is a complex number, a minus ib will be a complex conjugate. Now let us look at z bar. Actually at this point I don't want to look at z bar, but we'll see what happens. A plus ib into a minus ib. Actually I have not defined the multiplication, but we can easily see that this is a square minus ib whole square, which is equal to a square minus this is I square b square, which is equal to a square. I square is minus 1 by our definition. So this is minus 1 minus of minus plus 1. So this is a square plus b square. So z bar is a square plus b square if z equal to a plus ib. Let us, actually I have not defined the product of two complex numbers, but don't worry. This is, at this point we don't require anything. Simply it is a plus ib into a minus b, the formula which is a square minus b square. So let us let z1 equal to, I'll write down x1 plus iy1, a complex number, and z2 is equal to x2 plus iy2. Then the sum, how do we define the sum? The sum of two complex numbers is equal to, sum of two complex numbers is equal to, simply add component wise, x1 plus iy1 plus x2 plus iy2. This is equal to x1 plus x2 plus I times y1 plus y2. Again, this is of the form, simply this is some x, this is some y, so x plus iy, so z1 plus z2 is this, is again a complex number. Similarly, we can define minus. When plus is there, it has to be written minus. Now, let me write down z1 into z2. Look at this. I don't want to follow this now. z1 into z2 is x1 plus iy1 into x2 plus iy2 multiply. I'll get x1 x2 plus iy1 x2 plus x1 iy2 plus I square y1 y2. This is equal to x1 x2, I square is minus 1, so this is y1 y2 plus, take I common, so I will get I into, I will take x1 y2 minus plus x2 y1. It's again of the form a plus ib, so again a complex number. Now let us find the product. So z1 equal to x1 plus iy1 and z2 is equal to x2 plus iy2. Already we have calculated this as, this implies z1 z2 is equal to x1 x2 minus y1 y2 plus I times x1 y2 plus x2 y1. Already the product is calculated like this. Now let us see the quotient. If you want to write the quotient, obviously, see, whenever we are writing something like a by b, b should be different from 0. The denominator should be different from 0. So if you want to write down z1 by z2, obviously this is x1 plus iy1 by x2 plus iy2. Observe, z2 is non-zero. What do you mean by non-zero? z2 is non-zero means, let me write down here, that means x2 plus iy2 is non-zero. That means this is 0 can be written as 0 plus 0 I. That means either x2 is non-zero or y2 is non-zero. Non-zero means both should not be, need not be zero, non-zeros. Both should not be non-zeros. At least one is non-zero, that's fine. I can perform the quotient, perform division. Simply x1 plus iy1 into, I will multiply by x2 minus iy2 because already I have given about the complex conjugate iy2 into x2 minus iy2. Simplify this. You will get x1 x2 x1 x2 x minus y1 y2. Now carefully observe. This is iy1 into iy2. So when I am multiplying I by 1 into I by 2, I will get minus I square y1 y2. I square is minus 1, so minus of minus will become plus. Please follow this step carefully. Otherwise you can directly multiply this. Look at this, x1, x2 I have written. Now I want to multiply these two, I by 1 into I by 2. This is I square y1 y2, but I square is minus 1, but already there is a minus, so minus into minus will become plus, I1 by 2 plus I times. Now what is that? I times x2 y1 minus x1 y2. Because x1 into I by 2, I have I, so I have taken the by, multiply this, you will get x2 square plus y2 square. Separate it, x1 x2 plus y1 y2 by x2 square plus y2 square plus I times x2 y1 minus x1 y2 by x2 square plus y2 square. This is division of two complex numbers. I don't care about this kind of expressions. Simply we can follow in our own way. For example, let me look at an example. What is 2 plus 3i by 1 minus I? Remember, this is non-zero. So what I have to do is 2 plus 3i into 1 plus I, because I am multiplying by conjugate, 1 minus I into 1 plus I. Let me multiply 2 into 1, 2 plus 2i plus 3i plus 3i square by, this is 1 plus I into 1 minus I, which is 1 minus I square. A plus I b, a minus b into a plus b is a square minus b square, which is equal to 2 plus 5i, 3 into I square is minus 1, so you will get minus 3, by I square is minus 1, so minus of minus plus 1 by 2. So you will get minus 1 plus 5i by 2, which can be written as minus 1 by 2 plus 5 by 2 I. So quotient is again a complex number. We have seen product, we have seen sum, we have seen quotient. Minus is same. We need not worry about that. Now, very important aspect of thing is, look at this. Let P be any point in the real line. I mean, it's real axis, you can say. This is x, this is y. So this is r and this is theta. R is root of x square plus y square. When you are looking at in r square, let x equal to r cos theta and y equal to r sin theta. If you square and add, you will get x square plus y square is equal to squaring and adding. So r square cos square theta plus r square sin square theta, which is nothing but r square into cos square theta plus sin square theta, which is 1. So into r square is r square. X square plus y square under a root plus r minus is r. Thus, we consider only the positive root, positive square root. And what is y by x? R sin theta by r cos theta, which is equal to tan theta. So this implies theta is equal to tan inverse y by x. So any point Pxy on the real plane can be regarded as, what is x? R cos theta. What is y? R sin theta. So this is called the polar form. for any complex number, z equal to x plus iy, the polar form of z is, let me write down z equal to, what is x? I'm putting x equal to r cos theta plus I times y r sin theta. So this can be written as r into cos theta plus I sin theta. So this is the polar form for the complex number z. We call cos theta plus I sin theta as cis theta. Now, the definition for a complex number is given z equal to x plus iy, where x and y are real numbers, so square equal to minus 1. We are writing z equal to x plus iy, which is equal to r into cos theta plus I sin theta. That means r cis theta. So x is r cos theta, y equal to r sin theta. That is x equal to r cos theta, y equal to r sin theta. Then r is equal to plus root x square plus y square is called the modulus. So length, the positive length plus, we don't have a negative length. So it's called the modulus of z. And theta is equal to tan inverse y by x is called the amplitude. Or argument. So theta is an angle, is called the amplitude or argument of z. So r is a length, theta is an angle which is called amplitude. This is called r is called the modulus. Now after looking at r and theta, any point in the polar form is r comma theta. R comma theta means r is root x square plus y square with plus theta is tan inverse y by x, provided x equal to r cos theta by equal to r sin theta. Theta equal to tan inverse y by x. These are very two crucial concepts in complex numbers. We are writing the modulus of z and the amplitude of z. Now I would like to I would like to initiate with some of the properties. Before that, let me write down a note. Z equal to x plus iy. If z equal to x plus iy, then x is called the real part of z and y is called the imaginary part of z. X is called the real part of z and y is called the imaginary part of z. Also we write REZ, IMZ. This is a notation. Real z means x, im z means y, imaginary part of complex number. And one more note I would like to give here is x plus iy is equal to the real part, x plus iy is r cos theta plus I sin theta, and this can be written as r into e power I theta. This is what we know. E power I theta is here. E power I theta is cos theta plus I sin theta. So exponential representation of a complex number, e power I theta, cos theta plus I sin theta. If r is there, you will write r e power I theta. So this is r e power I theta. And the simplest task for this is x1 plus iy1 is equal to x2 plus iy2. Then x1 is equal to x2, y1 is equal to y2. Actually, this is, I can say, if and only if, a simple fact. That means x1 plus iy1 equal to x2 plus, if two complex numbers are equal, their real parts are equal, their imaginary parts are equal. So I would like to recall again how x plus, suppose x plus iy is non-zero. Suppose x plus iy is non-zero. What does it mean? This is 0 plus 0i. X plus iy is non-zero means either x equal to 0 or y non-zero. 1, first case, either. 2, either x non-zero or y equal to 0. 3, either, this is either. This is both x non-zero and y non-zero. So these are the three possibilities if a complex number is not equal to 0. Is equal to 0 means component wise x equal to real part equal to 0 and imaginary part equal to 0. But a complex number is not 0 means this is, that's what I have used in the quotient when I am writing z1 by z2.